Hello, my name is Julian Cecil. This is MEMS 5001, Optimization. My project was to optimize a Formula-style race car radiator. Washi Racing needs a new radiator. The 2016 radiator was too small. As a result, it wasn't able to keep up with the abusive condition on the track. This contributed to the car overheating frequently, and as such, had to stop the race car to allow it to cool down. I am interested in optimizing the radiator to prevent the car from overheating. Calculations for radiator performance are complex functions: engine RPM, ambient air temperature, coolant velocity, vehicle velocity, coolant fluid choice, radiator material choice, and radiator fin density. Engine thermal data was collected with Washi Racing's own dynamometer testing rig. The engine computer is able to log many variables at one time. However, the most important quantities to log were coolant temperature at the cylinder head, engine RPM, the temperature after the heat exchanger, and coolant flow rate. This is the dynamometer testing rig. It isolates the engine so that variables can be carefully controlled. The engine's coolant line is hooked up to a 4-pass shell end tube heat exchanger. These are the results from the dynamometer. The graph on the left shows 3 temperature probes at various locations in the coolant line over time. The right graph shows the engine RPM over time. These tests were conducted at wide open throttle, which is the most extreme case the radiator will see. 3 tests were conducted with the wide open throttle RPM the sweep to determine the maximum, average, and minimum heat rejection. Using Q equals m dot C sub P, delta T, the heat transfer out of the engine can be calculated. These values will be the fitness criteria for the optimization. The radiator size is limited by the race car side body packaging. The fin density is limited by commercial availability. The operating coolant temperature cannot exceed 224 long periods of time to prevent damage to the engine. The air velocity is between 0 and 51 miles per hour, which is a good drag strip acceleration run. The simplifying assumptions made in the code were that the ambient air temperature was constant. Thermal properties are constant. Only laminar and turbulent flow regions were considered. Radiator sizes are limited by commercial availability. And the radiator is angled perpendicular to the flow. The first step to optimization is to construct a virtual radiator. Each space between the radiator's fins is modeled as a cell. Then, based on commercial dimensions, the entirety of the radiator is modeled. The surface that the coolant sees and the surface area that the air sees is calculated for future computation. The optimization was then from knowing the properties of the fluids and the surface area of the radiator. The heat transfer and effectiveness can be calculated from the epsilon and U method for heat exchangers. The optimization was done in MATLAB. The radiator must be able to reject a maximum of 36 horsepower, while constrained by the dimensions and temperatures. It is a finite element solver that creates a single virtual radiator of a set size. It is then solved with heat transfer equations to calculate the maximum heat transfer. It is checked against the fitness criteria. It is rejected if it does not. Then the grid size is increased and repeated again until it passes the criteria. By working from smallest to largest, it assures that we get a radiator that is the smallest, which is also the lightest. The optimization results recommends that we buy an 8.19 inch by 13.97 inch radiator with 18 fins per inch. The graph on the left shows the heat rejection on the y-axis, the operating temperature on the x-axis, and the air velocity on the z-axis. The graph on the right is the radiator effectiveness plotted against air velocity. It shows the jump from laminar heat transfer to turbulent heat transfer at around 31 miles per hour. This is desirable because average track speed is about 35 miles per hour. This is where we would like to see the best performance.